now we're changing topics slightly, staying with sort of a perspective on other means of using nuclear reactors and integrating into other services. So I'd like to invite now Staffan Qvist, who is the director of Qvist Consulting. I guess it's not by chance your company is called the same as you. So you're a familiar face, I think, for many people who are working in this space in Sweden, but maybe not so often that we hear you talk about direct air capture. So I'd like to invite you to talk about that topic, and the floor is yours.
Yes, thank you very much for inviting me to talk about this topic and to make a chapter in the report about this topic. It's fun for me, particularly because it's quite novel. I am a connoisseur of literature, scientific literature from the start of let's say from 1950s and onwards, and basically everything has already been explored that I can come up with now by much smarter people than me. Wonderful works throughout the decades, but this topic specifically, in terms of nuclear beyond electricity, is actually not that well explored, which makes it fun to dive into and try to understand. So I will try to give a brief overview of what this means, what these words mean, and then how does it connect up potentially in the future to a nuclear energy generating facility. So let's try to get through. So direct air capture is in the category of technology of negative emissions technologies, or NETs, which is basically ways to suck CO2 out of the atmosphere. And I think I listed in the report something like 9 or 10 different ways to do this that people are proposing at various levels of commercial viability today. Planting trees is an obvious one that everyone understands, but there are many, many different other ways to do this. And why are these things interesting while we are still emitting CO2? Can be discussed. I will not focus on that topic, but rather explain this technology more deeply. But one can see that in the integrated assessment models that the climate modelers are doing, in almost all of them that meet some kind of target, be it 1.5 degrees of warming, 2 degrees of warming, or even larger warming than that, they still propose, and the model still requires quite significant negative emissions. So the extraction of CO2 out of the atmosphere. A typical one, I would say, for a hardline climate strategy, so say 1.5 or less than 2 degrees of warming, can be seen in the graph here, where the brown part is the positive emissions, which is things that we are emitting, and the yellow part is what they are assuming in the models, a typical model for what we will get, what we will extract out of the atmosphere by negative emissions technology. So this is a huge, huge assumption in the models, at least. And something in reality has to come and meet up that. Not just one technology, but a host of technologies has to come forward and become viable and be run well in order for us to do that. Otherwise, we need to cut emissions extremely much faster than we are today. And maybe even if we are doing that, we still need net negative emissions. So that's the general reason why we're looking at this at all. Now, direct air capture can be confused with carbon capture because essentially it is carbon capture. So direct air capture is just a way of saying carbon capture from air rather than from a concentrated source of CO2. So direct air capture is the way of saying that we can do carbon capture, but anywhere, not just on the flue stack of a natural gas power plant or a coal plant or a steel mill or something. And the big distinguishing factor, of course, is the concentration of CO2 in the gas that you're trying to extract it from, which might, on the face of it, make this look completely insane, because you have many coal plants running, very many natural gas plants running. So why would you try to suck out CO2 out of a source that's so much more diluted rather than put carbon capture on those plants? It isn't actually as different in terms of the effort involved in extracting the CO2 as it might look like from this graph. So as everyone is well aware now, we have an increasing concentration of CO2 in the atmosphere, but it's still kind of a trace gas. It's just not a very big component of the atmosphere. And so it is tough to selectively extract just the CO2. If we compare on a purely theoretical basis, and if you read the report, you see how these calculations are made as well. Just theoretically, from thermodynamics, how hard is it to extract CO2 from a source, given the fraction of that CO2 in the source on the x-axis of this graph? You see that a coal plant flue stack that might have anywhere from 10 to 15% of the gas that's coming out being CO2 is 300% more concentrated in CO2, but actually, at least on a theoretical basis, it only takes 3.5 times more work to extract CO2 out of the air than from that flue stack. So it is not as bad as it might seem on first look if you do the thermodynamics. There is also another aspect that significantly differs direct air capture from carbon capture, as it's defined, and that is that you can place it essentially anywhere. It doesn't have to be nearby a concentrated source of CO2. However, for economic viability, you can't really place it anywhere because you likely want to do something with the captured CO2. You either want to pump it on the ground, or you want to do something with it, maybe use a Haldor Topsoe CO2 to CO reducer and make syngas with hydrogen and make fuels or something. So you want to site it somewhere, so it's not completely free, but a lot more free than conventional carbon capture. Another thing that influences siting is water vapor, which makes it more difficult to extract the CO2 because the water competes for reactive sites on the sorbents, so it makes it less efficient to capture. Also, as I will explain, you need to heat whatever is capturing the CO2 needs to be heated up, and if it's full of water, that adds a lot of thermal mass. It takes a lot of energy to heat water, so that makes it worse. So there's a good thing you can find a place with dry air to capture from. So the overall very simplest way to describe the principles of a direct air capture system, it has 3 main steps. You have to move air somehow. You can either just sit around and wait for the wind to blow, but that is not the way direct air capture systems are engineered. You physically move air, typically with electrical fans, through the system at a controlled rate. You move this air past a sorbent or a solvent, so you get the CO2 from the air to react with something and stick to something. And then once it's stuck to something, you need to get it off that something to get it piped away in a high concentration form somewhere else, so that you can restart the cycle and move air again and get more CO2 stuck to your whatever thing you have that is capturing the CO2. So in a very dumb and simple way, that's the core of the process. There is, on the very highest level of interest in this discussion, essentially two technology pathways for direct air capture today, which depends on whether you're using a liquid solvent for the CO2 capture or a solid sorbent. So basically, are you using a liquid or a solid system for the middle step here? The rest is the same. You still have to move air and you still have to regenerate the chemical that captured the CO2. If we look at the first one, the liquid system, this is basically spearheaded and run by this entire technology option by Carbon Engineering, which is a very serious, very good company out of Canada that's trying to commercialize this type of DAC system. The main, I would say, issue of interest for the integration and powering by nuclear energy is that the regeneration of the solvent, so getting the CO2 away from the solvent, requires a very high temperature, basically to split up calcium carbonate into calcium oxide and CO2, a 900 degrees step part of the process, which in a sense limits the full heat integrations options for nuclear energy. So if you want to run the heat needs of the system only with direct extracted heat out of a nuclear system, you need to be able to produce heat higher than 900 C at the process site. This is possible. There are 2 ways that a nuclear energy system could power a liquid solvent direct air capture type system. One is obviously just electrical power, electrical heating, electrical fans, everything. But this is essentially agnostic to the source of that electricity. You could connect it to the grid or to anything else. So technically, I don't find it interesting to focus on that option for this study at least. Or you could supply the heat for every part of this process needed by a very high temperature reactor. There are two existing examples of reactors having been successfully operated that used primary coolant outlet temperatures high enough that they could supply 900 degrees process heat, which is the AVR in Germany and HTTR in Japan, which is actually still active and coming back into operation right now. The HDR-PM that was just started, the first unit in China, is designed for a lower outlet temperature currently, but it might be that you could, after verifying that it works well at that temperature, increase the temperature so that this could be possible. However, given the kind of limits of the options of the liquid solvent DAC system, the focus of this presentation and the report that I wrote was on the solid adsorbent direct air capture system, which is captured with a solid solvent, not with a liquid solvent. Again, and you can see here 3 of the main initiatives. There are probably 15 or so startups around the world doing this. Climeworks is the most famous one with the most facilities in operation. Global Thermostat is a partially oil and gas funded effort that's quite serious. Solitaire Power is a startup out of Finland that demonstrated doing this at the Dubai World Fair just recently. So this is happening. What is needed is, again, move air, capture the CO2, and regenerate the sorbent. Moving air in these systems requires electricity for electrical fans, and regenerating sorbent requires heat, and that heat is typically supplied also by electricity. So that's the situation we are looking at to start with. The energy requirements of these systems are quite difficult to pin down from public literature because most of them are stated as the targets for these systems in the future, not what they are performing at today. But you can do some fundamental analysis to figure these things out. For electricity, it basically depends on the pressure drop across the system. You need to move air and how much air you want to move through the system. And at what speed. You can calculate what the fan power would have to be. For the regeneration, it's basically all about how hot does the sorbent need to become to shed the CO2, and what is the, let's say, the heat capacity of that sorbent. So if the sorbent needs to go from room temperature up to 120 degrees C, and you know the heat capacity, you can figure out how many megawatt hours of heat you need to make that cycle happen. The rough numbers are maybe 0.5 to 1 megawatt hours of electricity to move air, and 2 to maybe even up to 5 megawatt hours of heat to regenerate the sorbent. So the system, and I might not go through this in full detail, but you can see this graph in the presentation and in the report, of the operation of such a system has basically 5 steps. So if we start from the top, point 1, you have electricity coming into a fan or a blower to move the air. You have incoming air, which is just normal atmospheric air, and you have the valve open, and the CO2 is captured in sorbent as it flows by. And on the back side of this system, you have CO2 depleted air. So basically air with less CO2 in it that comes out. Once the sorbent is saturated, it doesn't want to capture any more CO2, you close this unit. So you close the valves, and then you use a vacuum pump to empty out all the remaining air in that system. Then you heat this system up to the point, the temperature at which the CO2 wants to get off the sorbent and basically get shed. This is step 3. And step 4, you extract the CO2 that's been captured in a very rich stream, sometimes over 99%, maybe 99.9% even, depending on how well you did the vacuum at step 2. And then from the CO2 rich stream, I'm going to be agnostic of what you do about that here, but you will need to purify, compress, maybe liquefy, certainly transport it somewhere to do something useful with it or store it. Then the sorbent needs to cool down, either actively or passively, back down to a good temperature for it to capture, and then the cycle restarts. So those are the steps that are involved. Now, if we would want to power such a system with nuclear, and here I focus on light water reactor technology, there are two options. Either we could power a current day system that looks like this with a nuclear reactor and use steam extraction for the regeneration of sorbent, so the heating step. Second option is to optimize, so redesign this kind of system specifically for integration with a nuclear energy system. And that would mean both to use steam extraction for regeneration of the sorbent, but also to use heat, in this case waste heat, to, in a controlled fashion, move the air through the system. So you don't have to spend any electricity on fans. So I'll go through both of these. In both cases, as has been discussed a lot and will be discussed a lot in this topic, we want to extract heat rather than make electricity and then make heat again from that electricity. It's a lot more efficient to just take the heat if you have it. And the good thing about a nuclear reactor is it makes heat, and then you can choose either to make electricity with that heat or use the heat as it is. This is a picture of a typical, it's based on the EPR, but a typical turbine building kind of cycle. HP means the high pressure turbine, where the steam comes in first, IP intermediate pressure turbine, LP the low pressure turbines, and the red arrows and lines here is steam at various qualities, and the blue is liquid water. So what we want to do is tap in at 1 or 2 or 3 or more of the appropriate locations in the steam cycle, extract some of that steam out to a condensing heat exchanger, condense that steam into water, and then pump that water back into the feed water heating system at some appropriate location, while not impacting the safety case or the overall operation of the nuclear plant. So what is interesting from an economical standpoint here is how much electricity are we losing by doing this. So if we want to tap into a steam pipe here, extract some of that steam with a valve to an external heat exchanger, that steam that we took away from this cycle could have gone through all of these turbines and made more electricity and imparted more energy to the turbine blades and made more electricity. A rough way to calculate this is just to see how much electricity could that steam that you extracted have made, and that becomes kind of the opportunity cost of doing this extraction. So a simple equation for this is written here. Nu is the measure of efficiency. TR is the temperature at which we want to extract the steam. TC is the temperature at the bottom of this cycle, so at the outlet of the low pressure turbine. Over here, if you can see my mouse. So if we apply some typical numbers, maybe 0.78, 79 or so for the eta number, and 35 degrees Celsius or so at the bottom of the cycle, the only remaining variable here is how hot do we extract the steam, and P here will describe then how much electricity are we losing from extracting that steam. So for instance, if we want to heat a direct air capture sorbent to 100 degrees Celsius or so, a nice thing would be to use, at least in the Arabelle steam cycle, the T4 port in the low pressure turbine, which is at 105 degrees Celsius steam. And if we plug that in, we lose. So that steam has already gone through most of the turbine cycle when it gets to that point. So it has very little energy left to give to the turbine blades and produce electricity from. So you only lose about 1/7 of a megawatt hour of electricity for every megawatt hour of heat that you could supply at that temperature to something else. So in that sense, it's a very nice way, especially when you're far down the turbine cycle here, to make use of heat. Now, if you would like to power the direct air capture system, this is a schematic of how that might look like. And this is the regeneration of the sorbent. That's the important part here. So you extract heat out to an external condensing heat exchanger. You condense that steam by heating an external cycle that is heating the direct air capture system. The condensate you are reintroducing into the turbine or the steam cycle at the appropriate feed water heater for that condition. If you have a 3-stage extraction system and you want to get out something like 120 C, it's again about 1 in 7. So you get 1 megawatt hour of heat out usefully for 1/7 of a megawatt hour of electricity lost as an opportunity cost. If you only do 1 extraction, you might have to do that at a less optimal place, and the average temperature of extraction is higher, so you lose more megawatt hours per megawatt hour. A very strong limitation is, however, how much steam can you actually extract out of the system before you need to redesign it from the ground up. So can you go in, as Marcus was asking our previous speaker, and retrofit this solution into an existing plant, or do you need to make it ready for this from scratch? Our investigation show that up to about 10% of the thermal power of the plant can be extracted without any big problems. If you want to do more than that, you will probably need to make, stronger modifications to the entire steam cycle. And ideally, if you're building a new plant, you would design it for a higher, and that there's absolutely no problem to design it to be able to extract more power than that, but you would need to do that. So what is happening now, and this is not an announcement, it might not be very well known, but it's not secret information that I'm passing on to you, is actually there is a development going on for an optimized nuclear direct air capture system. These are on this slide are the participating organizations. So the process itself and the sorbents, and the substrate for the sorbents are developed by the University of Nottingham. Strata Technology is building a prototype and doing the engineering. Doosan and Atkins are working on industrialization and commercialization of this. And Sizewell C, which is run by EDF Energy in the UK, it will be the host and the supplier of utilities, so that's electricity and heat, and also project managing this project. So this is ongoing. The principle here is even stronger integration with the nuclear plant. So not only does this project envision steam extraction for regeneration of the sorbent, but also attempting to use the condenser cooling system as the way to move the air through the system. And that's based on the simple observation that the place on Earth, let's say, where you have the largest controlled continuous movement of air are cooling towers. Natural draft cooling towers just move a lot of air through them. That's how they're cooled, just by temperature difference. And so could we use the enormous amounts of low-grade heat, essentially worthless heat, used to cool the condensers of plants that use cooling towers, and redesign the cooling towers to actually be direct air capture systems? And so use that heat differential to drive the air through the system at essentially zero cost, because that heat has no economic value at the moment, but it would have if it could be used to push air through a direct air capture system. That is the principle that is being explored. And I should say this picture here with the direct air capture unit inside a cooling tower, this is not how it's going to look like. This is just to say the principle from things that we are familiar with. So the principle of a cooling tower that's used to move air will be used in this kind of system. So the engineering development, you can see a picture of the full 3D CAD model of this prototype that's being developed. It's a 100-ton CO2 per year plant that it has been designed. At the moment, it's designed to have electrical heating as a stand-in for what would have been nuclear cogeneration for heat, both to move the air and the heat to regenerate the sorbents. This proposal won the UK government direct air capture competition, so it's funded and it's ongoing right now. And maybe it could be a standard for SMR condenser cooling systems. Marcus, I see your face. Does that mean I'm out of time?
Yeah, good guess.
Yeah, okay. So I will just skip ahead. There are some assumptions here in tables that are boring for me to read for how much the equipment of direct air capture will cost. But the cost of capturing a ton of CO2 depends on the cost of the equipment, the cost of electricity, and the cost of the heat. The cost of the equipment, if you levelize it, depends very much on how much you use the equipment, as was also explained in the last presentation. If you use it all the time, it's going to be that part of the cost will be maybe a factor of 8 lower than if you use it 12% of the time. So this is quite important, the utilization factor of this equipment, which is quite expensive, which is nice for nuclear that runs almost all the time. If you want a dedicated facility, you can go back and look at these numbers. If you optimize a system for nuclear integration on both low temperature and high temperature heat, you can get the cost of utility supply for a DAC system down to something around a levelized cost of 17 euros per ton of CO2, we believe. That's from a reference production of electricity cost of 55 euros per megawatt hour, so quite conventional. If you do the same thing with only electricity, these numbers are far higher, even if your electricity LCOE is far lower, which is a result of the heat integration. So if we look at the final slide, how does comparative economics work out for systems like this? So low temperature, adsorbent-based direct air capture systems, the optimized nuclear DAC system, even if we assume its LCOE is twice that of, let's say, wind, which is the comparison here, it makes cheaper captured carbon. And that is because of the very high utilization of heat. It's mainly almost only using heat, which it can make fairly cheaply. There's a bunch of details here that we can discuss too. Conclusions, you can maybe reach down to 50 euros per ton of CO2 capture with a fully optimized system. And the resulting life cycle emissions would be something like a negative 160 grams of CO2 per kilowatt hour production of electricity. And maybe something like this could further develop, become kind of a standard solution for the condenser cooling system of SMRs, if it turns out the prototype works well. And with that, I don't know how much I overstepped my time, but thank you.
No, I didn't overstep it at all. It's just we riveted your presentation, Ian, and I wish I had more time for questions, but I have time for a few. So would you say that this kind of is this sort of a game changer for direct air capture?
It's in principle, it's similar to the geothermal powered direct air capture, which has been the front runner of applications so far. So the solid absorbent direct air capture systems that are in operation today are either connected to industrial waste heat or geothermal heat sources, and in principle, they are similar in the way that you would design them. They haven't used this kind of full heat integration. No one's proposed that before this project that I was talking about, which I was happy enough to be an advisor to. This is the direction this is going, I think. You want to do, this is a primarily heat requiring process. And so the stronger heat integration you can do and the closer you can get to a cheap heat source, the better this will work. And I think direct air capture looks quite hard in electricity systems modeling because typically it's not modeled as a heat integrated load.
And so the cost sort of assumptions or predictions or forecasts they see there are obviously impressive, but let's leave those to the side for a while. But you mentioned that that issue about retrofitting. So maybe you can just dive back into that. I didn't quite get how easy you think that could be done. And then related to that, what about the volumes here? You mentioned 100 tons a year, if I think for this project that you mentioned. But if you were to retrofit this to a sort of a conventional, say, a 1 gigawatt nuclear plant, how much CO2 would you actually be able to capture per year from that? So, just to get a sense of scale.
Yeah, so we made a study for the UK government as part of this competition to see that if you would, in theory, dedicate all of the plant's Sizewell C nuclear power plant to do only this and nothing else, So it wouldn't this would be its main purpose in life, let's say. How much CO2 could you conceivably capture? And that netted out, as far as I remember, roughly all of UK aviation emissions. So you could net out the conscience of UK flyers, more or less. And that was something like 35 million tons, I think, for that plant. It kind of a bit depends on how successful this heat integration on the lower end is. But you also are somewhat restricted at that scale by land, because since a direct air capture unit is depleting the CO2 in the air as it passes by, they cannot be placed next to one another, not after one another, let's say, in the direction of where the air is moving, which makes it a little tricky to site an enormous facility for this. That said, 1 million tons a year facility could be powered, and it would have a footprint of maybe 1 square kilometer, so 1 by 1 kilometer. In terms of retrofitting the steam cycle, we've talked to people who manufacture the steam turbines for light water reactors, and we came to the conclusion that once you do a big overhaul of the steam turbine, which you do, you replace stages of the turbines and you replace components in there periodically. If you time it with a major overhaul, you could introduce piping to extract something like 10% of the thermal power that's being produced without really influencing anything else too badly. You might have to submit additional documentation, of course, that this wouldn't hurt the safety case or anything like that. If you want to go above 10% of the heat produced in the reactor to be extracted, then you need further studies. It's physically done. There are nuclear light water reactor turbine cycles designed to extract up to 50% of the heat produced to external users. So the designs like that exist, but it would be more difficult to retrofit.
Right. I'm sorry to say we're out of time, Staffan. I would love to talk to you more, but not today. I'd just like to mention that the report that Staffan has been referring to is actually a forthcoming one called Nuclear Beyond Electricity, co-authored by Staffan, among others. That's going to be up on our website, the Energiforsk website, very soon. So I recommend you all to read that, and you'll be able to learn more about this topic and others that we talked about today and tomorrow. So thanks a lot, Staffan, for taking the time, and fascinating work as always. And I'll see you next time.